Hello and welcome to MiniLecture 21 on approximation. All right, in this lecture we're going to talk about how approximation is used in the life sciences and why it's particularly important in the mathematics of the life sciences. We're going to use a Taylor series to approximate a function, and we're going to describe how good or how bad our approximation is by talking about the error in the Taylor series. All right, so what is an approximation? In biology, there's two different reasons we might want to approximate a function. And the first one of them is that we need to have simple questions. So the questions in biology have to be particularly simple because the answer has to be simple enough that we can understand it and its biological implications. So we can't just get any old willy-nilly complicated answer. We have to have an answer that we can interpret biologically. So it's really important to either approximate the question or approximate the answer so that we can interpret the answer or interpret the question biologically. All right, so there are two different ways that approximations tend to come up in biology. The first one of them is to approximate a function, assuming, for example, that time is small. So we can assume that time is small. So as an example of where this comes up, suppose that you have a population that is growing, a population of size n of t, and you are harvesting it. So harvesting can refer to hunting or fishing or actual harvesting of plants. So suppose you're harvesting a population size n of t, and you want to know how long does it take for the population to reach a size of m. So here I've drawn m in red, and the black curve here is the population size. So we have the population size n of t, and we have the critical population size that we're trying to find is m. So we're trying to identify this point right there. Now, this curve here is really complicated, and it's hard to solve for when this complicated function here is equal to m. All right, so if we were to do that, we can actually get the true answer down here using a computer, but it involves tangents and all that kind of jazz. So what if we wanted to simplify something, so simplify this curve n of t to find a better answer? So we could simplify it by saying, well, suppose it gets there really quickly. So time is small. So suppose I only really care what the value of the function is when time is small. So we're over here on the left-hand side of this plot. One way that we could approximate the function is we could say, what is the best possible line that describes that function near the point t equals 0? So what if I approximate the function near t equals 0 with this gray line? How good of a job does that do? Well, it actually finds a root very close to what we would have found anyway. And so the gray is a good approximation. All right, the other way that approximations come up is if the rate is slow. So here I've plotted the root that you get here as a function of the harvesting rate h. All right, so how long it takes the population size to reach a size of m depends on how much of it you're harvesting. Well, it's a very complicated expression that we get there. So if we want to know what this expression is in order to interpret it for conservation purposes, one thing that we could say is, well, suppose that we are not harvesting too much. Suppose that we're harvesting a small amount of things, so assuming that the rate is small. So let's approximate this curve, assuming that the rate is small. Then we could approximate it as a line, this gray line, when that rate is small, and we get a linear expression in terms of the harvesting rate. So before we assumed that time was short, so we assumed that we were over here on the plot, so that time was short, and we got a linear expression in terms of time. Or we can assume that a rate is small, so something is only happens at a slow rate, and we can get a linear expression like this. How do we get that linear expression? Well, we're going to use derivatives, and we're going to get something called the Taylor series. So Taylor series are going to pop up everywhere in your life, and so I really encourage you to understand this as best as possible. All right, so a Taylor series approximates a function near a particular point. In this lecture, we're going to focus on it approximating a point near 0. So we're going to approximate it near 0 as a polynomial. So either a first order polynomial, a 0th order polynomial, a second order polynomial, or up to an nth order polynomial. Okay, so near the point x equals 0, the function f of x is approximately given by this polynomial here. So first of all, we have the intercept of the function. f of 0. So the easiest way to approximate a function at 0, so this is x equals 0, is to find the constant that describes the intercept at 0. So the first kind of approximation that we could use is a constant. That is just simply the intercept of that function. Let's move this down so it actually is the intercept there. All right, so the next way that we could approximate the function, and we're going to do this with an orange curve, is as a line. So we take our intercept and we add the slope of the function. We're essentially drawing that tangent line at 0. So we evaluate the derivative at 0 and multiply it by x, and this gives us the tangent line at 0, which you have found in a previous lecture. So this is the tangent line. Importantly, it's a line here, tangent line at 0. So the next way we could approximate it is as a tangent line. So a first degree polynomial. The next way that we could approximate it, we could make the approximate a little bit better by adding a quadratic. Because as we get out here, we don't do a particularly good job. And as we get out here, we really don't do a very good job because we're getting very far away from the actual function. So if we wanted to go a little bit further, we could approximate it as a quadratic equation, and we could approximate it like this. Oops, that did not work. Let's try this again. There we go. We approximate it as that quadratic. So how a Taylor series works is it approximates the function as different polynomials, originally a constant, a 0th degree polynomial. So we can either have a 0th degree, which is the constant, the first degree polynomial, or a second degree polynomial. You could add further degrees, but in this class we're going to really focus on the 0th, the first, and the second degree polynomials. All right, what does the second degree polynomial look like? Well, we wanted to have the same curvature of the function at this point right here, and so we're going to take the second derivative, set that second derivative equal to 0. Remember that when you take something that is squared power, you take the derivative of it, and that 2 comes down, so we got to get rid of that 2, so we're going to put that 2 right down in the denominator, so you have x squared over 2, and this is called a quadratic. All right, the nth degree term is a little bit more complicated. It's the nth derivative, so like the second derivative, you could just keep on taking derivatives and get the third derivative and the fourth derivative and so forth, and then you have x to the power of n divided by n factorial. So if you've never seen a factorial before, that's okay. What is a n factorial? Well, suppose we had 3 factorial. This is simply equal to 3 times 2 times 1. 4 factorial is equal to 4 times 3 times 2 times 1, and so forth. So n factorial is equal to n times n minus 1 times n minus 2, all the way times 1. So that's what a factorial is, and you got to divide by that factorial to get rid of the power rule. All right. This last term here is the error. So our true function f of x minus our approximate function f tilde of x is going to be equal to that error term r. So at some point x, r tells us how far we are from our approximate to the function, or this approximation to that function. All right, so the Taylor series approximates a function near a particular point. So for example, we have this Taylor series, which is our general Taylor series. Let's use it to approximate the function e to the x near the point x equals 0. So here is our e to the x shown in black, so the black curve here, and we are going to approximate assuming that we're over here on the plot. So maybe this is e to the t, and we're assuming that t is small, that time is small, so we aren't going very far. All right, so we have this little rate here. All right, so the first way that we can approximate it is as a constant. So if we evaluate e to the 0, that's this intercept here. We can approximate it as an intercept. If we do that, we plug in e to the 0 and we get 1. So the best way that we can approximate this as a constant is just to say it's this constant 1. All right, but the error in this is pretty big. Suppose we're out here, we have kind of a big error between this constant and the value of the function, and it gets worse and worse and worse as we go farther and farther away from 0. So if we want to make it a little bit better, we have to approximate it as a line. So we have our linear x term times the derivative at 0. So we're going to approximate it as a line, like that. We still have a lot of error in there, so we might want to approximate it even better as a quadratic. So we have our next term, so we have x squared over 2, that's that quadratic term, times the second derivative of e to the x, evaluated at 0. What's the second derivative of e to the x? Well, you have d by dx squared, dx squared of e to the x is equal to d by dx of e to the x, that's the first derivative. And then you take the second derivative, and this gives you just e to the x. Evaluating this at x equals 0 simply gives you 1. So we have x squared over 2 times 1, and that's this blue curve here. So this blue curve does a better job than the line, which does a better job than the constant. The error, this Rn of x to the n, this term is shown by this gray area. So the error between our approximation, the blue curve, and the actual curve at any point x is given by this distance here. All right. So let's do this again, but let's try it with the natural log of x plus 1. So let's approximate the function the natural log of x plus 1 near equals x equals 0. So the first thing we want to do is we want to approximate this black x log of x plus 1 as a constant. So we evaluate the value of the function at 0. So we're going to plug in ln of x equals 0 plus 1. So the natural log of 1, which is simply 0. All right, this isn't a particularly good approximation. If we use that, we'd have a huge amount of error out there. All right, so let's do a little bit better. Let's take x times the derivative. So let's find the tangent line here. So what's the derivative of the natural log of x plus 1? D by dx of ln of x plus 1 is equal to 1 over x plus 1. You'd have to do the chain rule, so you actually have a times 1 in there. And we're evaluating this at x equals 0. Plug in x equals 0, and you get 1 over 1 times 1 is equal to 1. All right, so we get that. So we have our line, which is 0, the constant, the intercept, plus the tangent line here, and we have this orange line. All right, so this is a better approximation. We're doing a better job at getting at that black curve, but we could do even better and to add the second derivative times x squared over 2. This is this quadratic term, and then we have our purple error. So we get better and better and better approximations as we add more and more and more terms to our polynomial. All right, so every approximation has error in it, this purple term. In the Taylor series, this is given by this purple term here. How do we find this error term? Well, we have the approximate value of our function, so we want to take the true value of our function and subtract the approximate of it, approximated to the nth degree. So suppose we want to calculate numerically the error in the approximation that we just did for the natural log of x plus 1 at the value of x equals 0.5. Notice that the magnitude of the error, the length of this purple area, depends on what x value you're using. So if you're using the x value over here at 1, you have this error. If you're approximating it over at 0.4, you only have a little teeny bit of error. So the magnitude of this term here depends on x. So what is that error term? Well, we have our actual value of our function, f of x, is approximately equal to this approximation, the second order approximation, f prime of x, plus the error term, r3 of x. Okay, so we have ln of x plus 1 minus x, we're going to move that x prime over to the other side of the equation to solve for x squared, is equal to r3 of x. So we have this, so r3 of 0.5 is equal to the natural log of 1.5 minus 0.5 plus 0.5 squared over 2. And if we plug all of those in, we end up with this equaling 0.0304. So going back up here, we're approximating the air right here. So what is the length of that purple area? And it's actually quite small. All right, with that, I'm going to let you try to practice using Taylor series to approximate the population when there is the population growth rate when there is a small rate of survival of juveniles to adults. All right, I'll see you in class.